Bless you. What Chapter 2.2 is verifying. Verifying that these statements are true. So what we're wanting to do for this first one here is to verify that secant squared of theta minus 1 over secant squared of theta is equal to sine squared of theta. This is what we want to prove. And to do this, we're either going to make the left side look like the right, or the right side look like the left, or if it starts becoming kind of too tedious to get one to the other, or vice versa, we bring them both down so that they're the same. The whole goal is to make the right side look like the left, left or right, or make them both look the exact same, or be the same. We're really wanting to show that they are equal. And to do that, we're going to use any and all of the processes that we have so far, any of the theorems that we had yesterday. So our Pythagorean identities, our reciprocal identities, any of these identities we're going to take into play. Now, for us here, we're really wanting to get to sine squared of theta. So, secant squared minus 1 and secant squared of theta. We can write these as sine squared or go in that direction. Now, looking at the top one here, we do have secant squared of theta minus 1. And this is referring back to our tangent and cotangent. Because I believe this is going to be 1 plus tangent squared for us here. I'm going to have to grab the... And I do have a photocopied sheet of these here that I will pass out to y'all that has all of our identities on them that we'll eventually get to. Because Malia, I gave you one, I think, last year, that double two-set page that had every single formula for it. And again, for those there, you'll be able to use them on the test. You'll be able to use those. So, and again, I'm not going to make you memorize every single one. Because once you finish this class, knowing all the Pythagorean identities is not going to be helpful. Yeah. So 1 plus tangent squared of theta is equal to secant squared of theta. And the reason that this is nice is because we can subtract 1 from both sides, telling us that tangent squared of theta is equal to secant squared of theta minus 1. So the numerator here, we can rewrite as tangent squared of theta. Questions on this so far? Now at this point here, and we have the denominator as secant squared of theta. Now at this point here, I'm going to stop writing equals sine squared of theta, because we know that I'm trying to get this to be sine squared of theta. And we're trying to verify it. So we don't, bless you, we don't know for sure, well, it should work out that they're equal. We're trying to prove that they are equal, that they are the same. So we don't have to rewrite equals sine squared of theta every single time. We just need to get this worked out to be there. Now we could have turned secant squared of theta also into what? Cosine squared of theta, 1 over cosine squared of theta, yes? Or we could go back and said, well, secant squared of theta is equal to 1 plus tangent squared of theta. Either works. I'm going to do the former and say that this is the same as tangent squared of theta over 1 over cosine squared of theta. Is we're trying to get to sine, yes? Sine squared? Well, these two are being divided, yes? Because we need to simplify it, so we're saying we're dividing 1 over cosine squared of theta. And I realize I probably should have done this in the first one. What is tangent squared? The fraction of sine squared of theta over cosine squared of theta. Now, when we divide two fractions, we don't actually divide. We can change it from division to what? Multiplication and flip the second. Theta over 1. Well, what happens here? These cancel, telling me that we have sine squared of theta. Is that what we wanted to prove? Yeah. And that's it. Questions on this here? Excellent. So we good with that there so far? Okay. I'm going to hit the reset. I'm going to do this one more time. Now, we started off with secant squared of theta minus 1 over secant squared of theta, yes? I can split this into two fractions because we have two things on top, yes? Because if we can add or subtract two fractions only if the denominators are the same, which means I could say that this is secant squared of theta over secant squared of theta minus 1 over secant squared of theta. Yes, we don't normally split fractions up this way, because when we deal with fractions, we're normally trying to get them to be 1, not 2 or 3, splitting them back apart. But the reason we do this is, well, secant squared of theta over secant squared of theta is 1, yes? Minus, if I wanted to simplify 1 over secant squared of theta, that's the same as what? Cosine squared of theta, yes? What do we know that 1 minus cosine squared of theta is? Sine squared of, and we're done. Yep. This is part of the frustrating part about these verifying. This is also why I'm not putting it on the test, and we aren't going to have a homework over this. Is there lots of different ways to get to the verifying to be able to verify it? Some take longer than others, but we still get there. And it's just using these identities and theorems that we have to try to get there. And I heard it best stated yesterday, it really feels like cheating what we're doing, because it's almost we're manipulating these formulas to get them to work the way that we do, or the way that we want. Because all the way up to this point, in any math class you've had, we had a formula, it worked this way, this is the way you use it, we don't use it in any other way. And then you get to this point here and like, oh, we can manipulate this formula however we want, and we're going to do it to whichever way we want to make it work best for us, which hasn't been true in any other area. Any other questions on this here? Let's look at the next one here. We have 2 secant squared of alpha is equal to 1 over 1 minus sine of alpha plus 1 over 1 plus sine of alpha. Now this one here, because the first one we did, we manipulated the left side of the equation to make it look like the right, yes? This one here, we're going to manipulate the right side to make it look like the left. Because trying to get 2 secant squared of alpha to look like our two fractions is going to be a little bit challenging. And again, with any of these here, the first line or the first method I would look at is whichever one you can see or feel like you can actually work with to try to get it to be the other side. Because trying to find a spot to start with 2 secant squared of alpha is kind of hard to see where we're going. But the other side, I have 2 fractions that are being added together. Yes? So we can do that. But to get us to be able to add these two fractions, we need the denominators to be the same, yes? So for the one on the left, we're going to multiply it by 1 plus sine of alpha on top and bottom. And for the one on the right, we're going to multiply by 1 minus sine of alpha. Questions on this so far? And even on the midterm, if you're just manipulating one side to get it to look like the other, this is how I actually would do it. I wouldn't even rewrite 2 times secant squared of alpha. Because if that's where we're going, as long as we can show that this side is it, we don't have to rewrite that they are equal. Now we multiply these two here. The numerators are quite nice because we have 1 plus sine of alpha and 1 minus sine of alpha, yes? The denominators are actually quite nice as well. Does anybody know what they would multiply to be? Well, we have 2 of the same things, yes? Because we have 1 and 1 match up, same spot, sine and sine match up. The only thing is the signs are different, yes? When we factored a squared minus b squared, we got what? A plus b times a minus b, yes? So it's really the first term squared minus the second term squared. If the numbers are the same, the only thing is difference the signs. And we like those, especially with factoring, yes? Difference of perfect squares. It works going the other way. Because these here are a difference of perfect squares, yes? So that means we're going to get 1 minus sine squared of alpha. If you notice that they are pretty much the factors for the difference of perfect squares, be the first term squared minus the second term squared. Same is true here. Questions on this so far? Now again, at this point, we can add 2 fractions. We know the denominators will stay the same whenever we add 2 fractions or subtract 2 fractions. So we'll add the numerators. 1 plus 1 is, sine plus negative sine is 0. So we have 2 on top, yes? Okay. And we're trying to get to what? Secant squared, yes? Well, secant squared is the same as 1 over what? Cosine squared, yes? So we'll need cosine. Well, 1 minus sine squared is cosine squared. So what we really have is 2 over cosine squared of alpha, yes? Well, we just have 1 step left. Because if cosine squared's in the denominator, we can rewrite this as 2 times secant squared of alpha. I will take that. I mean, some professors might not like that. They might like you to rewrite it as an in-between step as 2 times 1 over cosine squared of alpha. Because noticing that the 1 over, we flip it to get there, but still the same thing. Questions on this here? Because even if you got to here and got kind of stuck on how to do that, well, the other side we had was what? 2 secant squared of alpha, yes? Well, that's going to be times now I've got the 2 sides to be the same, and we're done. Does that make sense? Now, we'd only really do both sides to a certain point is if you get to something like this here and are absolutely stuck, have no other way you can see to go, then we can see if we can turn the other one into that same form. Because again, we're just trying to show that the two sides are equal or the same. Questions on this here? We want to verify that tangent squared plus 1 times cosine squared minus 1 is equal to tangent squared, negative tangent squared. Where do y'all want to start? So if y'all were looking at this, where would you guys start? Start with the left side, yes? So, I mean, there's different things we can do. We could use the fact that tangent squared of x plus 1 is secant squared, but that's not really helping us much because we need to get to tangent. Cosine squared minus 1 is the same as sine squared, but I don't know if that'll help us much. But we do have two things multiplied together, yes? Just want to multiply. Tangent squared times cosine squared. Tangent squared of x. Cosine squared of x. Tangent squared of x times negative 1 is negative tangent squared of x. 1 times cosine squared of x is going to be plus cosine squared of x. And 1 times negative 1 is negative 1. Well, that was kind of nice. Because that there is what we want, yes? Now we just need to find a way to get the rest of it to go away. Now we have minus 1, yes? So what's a number that would cancel out with minus 1? Plus 1, yes? Do we have any identities that are 1? We have 3, don't we? Because we have tangent squared plus 1 is equal to secant squared. We also have that cotangent squared plus 1 is equal to cosecant squared, yes? So we do have both of those. And our third one is what? Sine squared plus cosine squared equals 1, yes? Well, we already have a positive cosine squared. But if we had a positive sine squared, we'd be done, yes? What's the other thing that's kind of making things a little bit difficult? This here, yes? What's tangent squared the same as? Sine squared over cosine squared, yes? So if I rewrote this as sine squared of x over cosine squared of x, it's also being multiplied by cosine squared of x minus tangent squared of x plus cosine squared of x minus 1. Let's see what happens. Well, hey, those would cancel out, yes? Because we would have sine squared times cosine squared over cosine squared. Cosine squared over cosine squared would cancel, leaving us with, scroll up, sine squared of x, yes? Wait a minute. Sine squared and we put minus 1. We now have one of the identities, don't we? Because this here is 1 and that's it. That's all we had to do. So this one here, just going on and doing the multiplication, kind of did help us get there. And again, on a lot of these, it's just looking at the identities and seeing which one am I going to need to use, or which one's going to be helpful for getting where do I want to go. Questions on these here? Are you ready for another one? Tangent times cosecant of x is equal to secant of x. Okay. Where would y'all want to start with this one? Yeah, so tangent sine of x over cosine of x. And this is being multiplied. Well, cosecant is 1 over sine of x, yes? Which is? That's it. What if I told you we could do this in one step shorter? Now at this point here, we've not really, all I've got to do is back up to here. We've not done a two-sided verify up to this point, yes? Well, we could say this equals what? 1 over cosine of x, yes? Which after we multiply, we have 1 over cosine of x. Show that both sides are the same. And that's it. And this is why doing both sides is sometimes helpful, because on some of them, not too many that we'll encounter, there are some that when we get the one side simplified down or tried to get it simplified down, it got a little bit complicated to try to untangle some of it. So sometimes it's easier to pull the other side down to that somewhat tangled mess and show, okay, we can get both of them to this spot, so they are the same. And that's all we did here. Luckily, this wasn't as bad. Questions on this here? Can anybody spot the typo? Because this should be a E. I put these up because I don't like having to write on it, but it does have a math writing spot. And I didn't notice that till later. So we have secant of x, and I don't know why it's just in parentheses, minus sine of x equals cosine of x times cotangent of x. So we're trying to get from one to the other. Now, which side do we want to start with first? I want the other arrow. We could think of this as a brick wall and do both. You don't have to draw the dotted line. We kind of work with both sides and see where we get. Now, for the right side, well, cosine times cotangent squared. We can say cosine of x times what cotangent is, cosine of x over sine of x. And if we multiply these together, we get cosine squared of x over sine of x. Okay. I mean, that's not too bad. That's just using some of our basic identities, yes? And I mean, we could take it further from here because cosine squared is the same as 1 minus sine of x, sine squared of x. But that might be helpful, that might not. We don't know at this point. And especially if we're trying to get to secant of x minus sine of x, yes?
May I have your attention? May I have your attention, please? Thank you.
Now let's look and see what the other side is. So secant of x is what? 1 over cosine of x minus sine of x. Now if I wanted to subtract these two, I need the denominators to be the same. So we'd have to multiply this by cosine of x over cosine of x. Yes, that's what I was afraid of. This here was a typo, but all the correct letters are there. So do you know what this is actually supposed to say? Yeah. CSC of x. I was feeling like that was looking a little weird. Because for us, what we're looking at, and the reason I knew to kind of look back at this is the left or the right side had a denominator of what? Sine, yes? And with that multiplication, it was guaranteeing us to have a denominator of cosine. That was not going to work. Because here, CXC of x, the denominator should be sine. Okay. Now we can get the denominators to be the same by multiplying this one on top and bottom by sine of x over sine of x, which would give us 1 over sine of x minus sine squared of x over sine of x. Y'all starting to see how we're going to put these two together? Because now the one on the left, the numerator is 1 minus sine squared of x over sine of x, yes? Well, what's 1 minus sine squared of x? Cosine squared of x over sine of x. The two sides are now the same, yes? So we're done. Questions on any of this here? Let's look at the next one. Cosine over 1 minus sine of x equals secant plus tangent of x. Yeah. Secant plus tangent of x. Okay. I was hoping it would let me update it, but nope. That extra C is not supposed to be there. Now, for me, I can't see too much that we can do with the cosine over 1 minus sine of x. because a lot of our identities, the main ones we use, are the Pythagorean identities. And all of those deal with having something squared, yes? So I would look at this side over here, secant and tangent. Well, everything on our left side is all in the form of sine and cosine, yes? So let's get the other side there. Secant of x is 1 over cosine of x. Tangent of x is sine of x over cosine of x. We can add these together and we get 1 plus sine of x over we get this here, yes? Now what is cosine squared of x? 1 minus sine squared of x. And we have 1 plus sine of x on top. Yep. So we have this here, yes? Well, we could factor the denominator to 1 minus sine of x times 1 plus sine of x over 1 plus sine of x. Let's see how. We got the cosine. That works too. Secant tangent. I'm just making sure I didn't miswrite this again. Nope, we're good. Okay. These would cancel, telling us we have 1 over 1 minus sine of x. Make sure I didn't do something funky. Yep. Plus that is where I lost my mind, right there. What happens when we add two fractions? Can anybody else tell me what went wrong here? I squared it. Did y'all see that there? If any of y'all need an eraser, I have some. Anybody need one? Okay. Yeah. Because the rest of this is just So we get to this point here, yes? Because what I was wanting to do would have been nice is if we had cosine squared on bottom, yes? Okay. So what we're going to do now is actually get that by multiplying top and bottom by cosine of x. Which, okay, now we do get cosine squared of x on bottom. Now on top, we can distribute that cosine of x. But we already saw that there's a way to get rid of it, yes? The 1 plus sine of x. I'm going to leave it in this form here. Now, if you went on and multiplied it, that's fine. But the reason I left it unmultiplied is that we have cosine of x times 1 plus sine of x is over 1 minus sine squared of x.
Logan Keaton and Brendan Fowler, please come to the office. Logan Keaton and Brendan Fowler.
Now, we can factor the denominator, like I was trying to do earlier, and getting confused why it didn't work. Now they do indeed cancel, telling us that we have cosine of x over 1 minus this here. Questions on this so far? Okay. So we have two left. We have this one here, 1 minus sine of x over sine of x, and cotangent squared of x over 1 plus cosecant of x. Now, cotangent of x, we could rewrite as, flipping back to look at our identity just to make sure. Yep, 1 plus cotangent squared is equal to cosecant squared of x. So what we could do with the left side is rewrite cotangent squared as cosecant squared of x minus now cosecant squared of x minus 1 is the difference of perfect squares. And the denominator we could rewrite as c of x plus 1. These two here will cancel, telling us that we have cosecant of x minus 1, yes? You all see a lot of options we can go from here. I mean, we could try rewriting it as sign here, as we could go 1 over sine of x and then try to add those together. Which would give us 1 minus sine of x minus 1. Okay. But looking back at the top one, the sign is negative, isn't it? So we'll see. if I want to actually combine these two, I need the denominators to be the same, yes? So for 1, it's going to be sine of x over okay, we got where we wanted to be. Any questions over any of this here? There is no homework. And again, with a lot of these here, and especially on the midterm, I'm going to be very nice with the grading on it. Okay? So again, try any of the methods that you think would work and then go from there. I don't